Okay, so I kind of wanted to give you an idea of what this, what it means to trace out this epicycloid. So imagine you have a circle, and you've got a large circle, has a radius of 4, and you've got a little tiny pink circle, and the pink circle is rotating around the big circle. Okay, so now imagine if you just keep track of, we're going to just keep track of, say, this little outer little dot on the pink circle. Now, as the pink circle rotates, so imagine the pink circle is rotating, this little dot is going to come in, right? And at some point, that little dot is going to touch. So I hope I'm doing a good job here, kind of. Um, it's like as it's rotating, this green is going to rotate as well. So it's rotating and it's moving forward. And basically, the how we're tracing out our brand new curve is by keeping track of this little dot. And so this little dot is actually going to form kind of, they look very similar to semicircles, and of course they're not going to be jagged, so perhaps it's better for me to just say it's going to look like this, right? They're going to look like this, and then finally it's going to get back to its original position, and it won't even necessarily be that many little touches, right? So how many times is that little dot going to touch our big purple circle? Well, it depends on the circumference of the big circle versus the circumference of the little circle. So because we've got this 4-to-1 ratio, we are actually going to have the big circle touched exactly 4 times by the little circle. So let me be more accurate here. So sorry, I kind of erased everything, but so our little circle is going to touch like 4 times. 3, 4. Okay, all right. So our focus is figuring out the distance that that little point travels in one complete trip around the larger circle. The first thing we need to do is we need to figure out, we know we're going to use this formula for arc length, but we need to figure out A and B. Okay, so the question is, for what values of t do we start off with this point here, say? Maybe we're starting here. And then we said we know it's going to hit 4 times 1, 2, 3, 4, and then come back. But now what are the values of t for this? Okay. If so if the point is going to touch the purple circle 4 times, then here's what will make sense. Instead of computing the length sorry, I thought that my video stopped here. But instead of computing the length for 1, 2, 3, and 4, we could just compute the length of one bump and then multiply that by 4. So that's the first simplification we're going to make, is that we're going to say that our L is equal to 4 times the integral, the arc length, just around 1. So imagine what is the length of just one of these petals, if you will. And now to find out what's the range of t, we can use some reasoning to say that as t goes from 0 to 2 pi, we would be drawing out the entire circle. So take that 0 to 2 pi, and we can divide it by 4, and say we're going to go from 0 to pi over 2. So we'll let a be 0, and b is pi over 2. Now we just need dx dt. We're given x is 5 cosine t minus cosine 5t. So dx dt is going to be minus 5 sine t, okay, plus 5 sine 5t. And dy dt, similarly, is going to be five cosine t minus 5 cosine 5t. Okay, so we need dx dt squared, which is going to be minus 5 sine t plus 5 sine 5t, quantity squared, and dy dt, which is going to be 5 cosine t minus 5 cosine 5t, all of that squared, dt. Okay, and oh yeah, just to mention, we are satisfying the restriction or the requirement that C doesn't intersect itself, because our curve isn't the curve just doesn't intersect itself. We're only taking into account one trip around the circle, the larger circle, so we're good with that requirement. Okay, so let's do some algebra here. So in the bottom, I can pull out well, let me just go ahead, actually, instead of trying to do shortcuts. So I'll have 25 sine squared t, okay, minus 50 sine t sine 5t plus 25 sine squared 5t. And then over here I'll have plus 25 cosine squared t minus 50 cosine t cosine 5t. Okay, and then plus 25 cosine squared 5t. Okay, equals, and we have 4, and then the integral from 0 to pi over 2. And now let's see here. 25 sine squared t plus 25 cosine squared t, that's going to equal 1. So we have 1. And we can do the same little, use the same trig identity to rewrite 25 sine squared 5t plus 25 cosine squared 5t. Okay, so we'll have 1 plus 1, and then all of that multiplied by 25, right? Because we need to factor out the 25. So sine squared plus cosine squared is 1. And then again, factor out the 25. Sine squared plus cosine squared is 1. Okay, and then minus 50 times sine t sine 5t minus 50 cosine t cosine 5t. And then the square root of all of that, dt. Okay. Now, let's see here. It looks like we can pull out a factor of 25. So if I factor out 25, and then I'll have 2 minus 2 sine t sine 5t minus 2 cosine t cosine 5t, and all this dt. Okay. Now I can, I can write this as the square root of 25 times the square root of this. And then what is the square root of 25? It is nothing other than 5. So this 5 times the 4, right? So we should have this 4 on the outside. 5 times 4 is now going to give us 20. So we can have a 20 on the outside. And on the inside, let's see, we've got 2 minus 2 sine t sine 5t minus 2 cosine t cosine 5t. So 2 minus 2 times sine t sine 5t plus cosine t cosine 5t. Now, does this look familiar? Here's a hint. The hint is another trig identity. And our trig identity is going to be that for cosine of 2 theta. So on the side here, I'm just going to say recall cosine of 2 theta is equal to cosine of 2 theta is 2. Hold on, wait. I'm thinking it's cosine of 2 theta. 2 cosine theta sine theta. Let me see. What about cosine of a plus b? That should be cosine a cosine b minus sine a sine b, and then sine of a plus b is sine a cosine b plus sine b cosine a. Okay, what do we have here? So we've got sine and cosine together. I would love to let's see here. I need to double check. I need to verify my, because I'm not sure if this sine and, I think, let me double check my trig identity here. Okay, so if we've got cosine a plus b formula, let's just look at this. Okay. So, okay, got it. I was very, very close. I just Googled it. I was very, very close. The key here, the key is to remember that we can use the sign of our trig functions to say that cosine of a minus b is going to be cosine a cosine negative b minus sine a sine negative b, right? But now cosine is an even function, so cosine of b negative b is the same as just cosine of b. And sine is an odd function, so sine of negative b is the same as negative sine b. The negatives cancel each other out, so we've got cosine a cosine b plus sine a sine b. So here, down here, that's what we want. We want to say, so we've got cosine a minus b is equal to cosine a cosine b plus sine a sine b. So our a is going to be t, and our b is going to be 5t, right? So we should replace this with cosine of a minus b, t minus 5t, which is the same thing as cosine of negative 4t. But remember, that's just going to be the same thing as cosine of 4t. Okay, so let's go ahead and write this on a new page. So we need 2 minus 2 cosine 4t, square root, integrated from 0 to 2 pi, and multiply it by 20. Okay, so let's add a page below. So L is equal to 20 times the integral from 0 to pi over 2. We've got 2 minus 2 cosine 4t, and we've got the square root of that, dt. And now we've got actually another trig identity that says, let's see here, so this trig identity, what is 1 minus, cosine 2 theta over 2, that should be equal to sine of sine squared of theta. I believe, let me just verify this. This is called the double angle. I'm trying to figure out how to Google this. Sine squared . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . let's see here. I think so. Okay. So yeah, so cosine minus. So this is good. Okay. So this is correct. This is correct. This is a. I verify that this identity is correct. Let me just to verify. Cosine of 2 theta is equal to cosine squared theta minus sine squared theta. True. 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 And cosine squared theta plus sine squared theta minus 2 sine squared theta is going to be equal to cosine 2 theta. Right, all I did was add in a plus sine squared theta minus sine squared theta. Right, now this I can group together because that's just going to be equal to 1. And now I've got minus 2 sine squared theta is equal to cosine of 2 theta. And so now 2 sine squared theta is 1 minus cosine 2 theta. So divide both sides by 2, and I get sine squared theta is equal to 1 minus cosine 2 theta over 2. Sine squared 1 minus cosine 2 theta over 2. Okay, good. We're good, we're good, we're good. Okay, so this problem is turning out to rely a lot on trig identities. So make sure that you have your list and you kind of freshen up on those trig identities because they come in handy when you're doing arc length. Forgot about that. Okay, so do you see how we can, so here we are. So L is going to be equal to 20, 0 to pi over 2. Now I'm going to pull out that 2, square root of 2, times the square root of 1 minus cosine 4t dt. Now the 1 minus cosine 4t, that's the same thing as cosine of 2 times 2t. Hey, you want to just barge in? No problem, no problem, coming in. So I have 1 minus cosine of 2 times 2t. We still got that square, we can pull that square root of 2 on the outside. Okay, and so now this is the integral from 0 to pi over 2. We've got the square root in here, dt. I want to get it to be 1 minus cosine, you have 1 minus cosine of 2 theta is now equal to 2 sine squared theta. So 1 minus cosine of 2 times this is equal to 2 sine squared 2t. Do you see that? Okay, now I've got the square root. Okay, so I can again pull out a square root. So I've got a square root over here. We know what's going to happen. Right, so we'll end up with just 2, so that'll be 40 times the, well, let's go ahead and move down a little bit. 40 times the integral, 0 to pi over 2. And then we can take this to just be sine of 2t dt. And what is the integral of sine of 2t? Cosine 2t over 2. And then I need a factor of negative 1. I need to evaluate this at t equals 0, t equals pi over 2, and then multiply it by 40. And when we do this, we should get, let's see here, so that'll be negative 20 times cosine 2t, t equals 0, t equals pi over 2. And we'll have cosine of pi minus cosine of 0 times negative 20. And cosine of pi is, what is cosine of pi? Negative 1 minus cosine of 0, which is 1. Okay, so this should give us negative 2 times negative 20, which should be 40. All right, so that is the arc length. And in fact, if we, let's see how reasonable is this. So if we've got our little circle here and our big circle has a radius of 4, then and we've got our little circle, which is radius of 1, and we said we've got a point, and that point is just going to go around the circle 4 times. How reasonable is it for that arc length to be 40? Let's see here. So what is the circumference of this circle? Our circumference is going to be 2 pi r. So r is 4, so 2 pi times 4, which is 2 pi times 4 is, that'd be 8 pi. Pi is like 3, a little bit over 3, so that's about 24. Okay, a little bit bigger than 24. Now, if we now take into account that we have imagine now we've got a bigger circle. Sorry. So we've got this 4 plus this 2. Now just think about if we just think about, okay, this is what I want to say. What I want to say is imagine that you take the circle, and instead of rotating the inner circle, if you just shift it, right? So you just take it, let me see. You just move it, shift it, shift it, shift it. What you would end up with is you would end up with that same point moving, and how far would it travel? It would travel the circumference of this larger circle. And what is the radius of this larger circle? 4 plus 2, which would be 6. And so now our new circumference would be 6, 2 pi times r, so 2 pi times 6, which would be 12 pi, which is about 36, a little bit more than 36, which is close to the 40. Okay, so seems like we did it correctly there. So I just wanted to point that out to you as well.